This is a rope driver module from my Block 2 Apollo guidance computer. And as you can probably tell, something is wrong with it. And so today, I'm going to try to figure out what. Now, there's nothing obviously mechanically wrong with it. It's in really good shape. And so I suspect that the issue is more likely to be electrical rather than mechanical in nature. And so what I've done is I have printed out the procurement specification, which has acceptance tests. We found most of this in the National Archives, and I'm just going to run through the tests to see if I can figure out what's wrong. Now, I will say, right off the bat, it is possible, perhaps even likely, that I won't be able to figure this out. And the reason I say that is that this module was tested both under normal conditions, but also under voltage extremes, temperature extremes, and under vibration. And so if it failed for any of those reasons, I'm not going to be able to know because I don't have the capability to run those tests. And even if I did, I probably wouldn't want to do them to an artifact like this. So we'll find what we find or not. The other thing that makes me say I might not be able to figure this out is that this is actually the second scrapped AGC module that I have played with. The first one was an actual core rope memory module that had some Apollo 8 software in it. As many of you watching this probably already know, a few years ago I built a core rope memory reader, and I had the opportunity to plug that scrapped rope module into my reader and dump it, and it read perfectly fine with no issues. So I don't know what was wrong with it. And even though there's nothing obviously physically wrong with this, that doesn't necessarily mean that the fault must be electrical. It might not even be a fault. It could be something bad that happened in this module's history. For example, it's possible that they just dropped it and then decided that rather than risking an entire mission on a critical piece of hardware that's been dropped, they would simply replace it. Something else that I find interesting physically about this module, by the way, is this red scrapped module text, which seems to have been a Raytheon-specific thing. For whatever reason, even though most of the markings on this module were standardized, that scrapped module text seems to have not been. AC Electronics, the manufacturer for other pieces of the guidance system, like the coupling data unit and the signal conditioner assembly, tended to use big yellow letters that said discrepant for items that failed for whatever reason. Something else notable is that very often on failed modules like this, you will see a dig site where they went in and they tried to understand exactly what happened to cause that module to fail. And that is notably lacking on this rope driver module. Or so I thought, until I was taking a closer look at it. And I spotted some scratches that seem to surround a section of potting material that is darker than the rest of it. And when I saw that, I took a closer look over the rest of the module. It turns out that opposite that, there's a little circle that originally I just thought was like a bubble or something. Immediately opposite this one that has these scratches. And looking down the length of the module, there's two more. And if we flip it over, again, two more that are exactly opposite these two. And so that makes me think that actually they did go digging in this module, and they either found the fault or not. Maybe they fixed it. But then, for whatever reason, they decided to fill the holes back in and then proceed to use it for engineering use, I suppose. But maybe they used it in some Apollo guidance computer on the ground. Maybe it sat on the shelf, and that's how it ended up with me. But the fact that they were digging is very interesting. The construction technique used for these modules was known as cordwood, in which a whole bunch of through-hole components are bundled together, sort of like a cord of wood, for maximum packing efficiency. And then the leads, which are sticking out either side of the bundle, are interconnected with wires to form the circuits. In the case of the Apollo guidance computer, to make these interconnections as reliable as possible, they actually welded nickel ribbon between the leads instead of soldering wire. And that made for very reliable connections. Now, obviously this module is potted, so I can't really show you what that welded interconnection looks like aside from this little piece of the signal conditioner module. But what I can show you is what a rope driver module looks like when it's not potted. This is a module from the Apollo guidance computer that we restored for the 50th anniversary of Apollo 11. This isn't the exact same model, it's an earlier revision of this module, but it should be very close in layout to the rope module that I have here. And so it can give you a little bit of an idea of what is going on inside, which is handy to reference, but we can actually get more scientific with it because of all of the resources that the National Archives has in their collection. Among those things are assembly diagrams of these modules that show where all of the components are placed and how they're interconnected. And so what I'm going to do is I'm going to measure out exactly where those dig sites are on this module and draw them on this diagram, and hopefully in doing so I'll be able to isolate exactly which components they were digging on, and then from there we can cross-reference that with the schematics to figure out what circuits maybe have been affected by the fault. So I'm going to get to measuring, and I will let you know what I find. All right, I took an initial measurement, and the scale of this drawing is about 1.25 to 1. So I have to multiply all the measurements I take here by 1.25. So let's get going. Okay, first dig site. I think you can probably see it here. This is a transistor that they were after, which is actually not really what I was expecting. It means that this is the one that was opposite the big one with all the scratches around it. And so they were not after a component that went through to both sides. This is a three-legged transistor, and all of the leads come up this way. Yeah, okay, so this is Q8. This is our guy right here. It is one of the components that they were digging on. Very interesting, not what I was expecting. And I'm very curious what circuit that's a part of, but we'll find out in a little bit. I'm gonna keep going. Okay, this one is a little bit less clear to me here. This is interesting for a couple reasons. First, it seems like it's mostly centered on the inductor L6. The resistors 6R26 and 6R27 also appear to be within the window there. But also it reaches up to the nickel ribbon interconnect, which is something that's not present in all of the cordwood modules in the Apollo guidance computer, but it is present on some of the more complex ones. Essentially, instead of running feed-through wires back and forth through the middle of the module, they mounted a nickel ribbon interconnect along the top of it, and then put the top of the module over that. It's not removable when the whole module is potted, but I did remove the top lid, sort of the top of the module, from the AGC that we restored. And so this is what that looks like. The fact that they extended this hole up high enough to see the connection to the ribbon interconnect perhaps suggests that they were unsure if the fault was on these components or within the interconnect. It looks like the other dig site on this side is also going to reach up that high. So very interesting. Let's keep going and see what else they were digging on. I suspect, just eyeballing this, that they were after the other inductor here, L4. I think that's what we're going to end up looking at. Okay, and as expected, they were digging on L4, and possibly also 2R26 and 2R27, just like they were over here. So consistency is good. The really interesting thing about L4 and L6, just looking at them and what I know about the rope module, is that these two are unlikely to be in the same circuit. I think that these are essentially unrelated inductors. And so the fact that they were going after both of them suggests that, I don't know, multiple faults is usually unlikely, and so maybe they were going after an unexpected low impedance between the two or something like that. That'll be something to look for on our resistance checks. All right, moving on to the other side. Let's see what we have. We'll save the big one for last. All right, as expected, we're looking at L4 on the other side. Also notable is that on this side, the digging has gone all the way up to the top layer here, but there isn't a connection to the nickel ribbon interconnect on this side other than this connection from 3R26 going up. So it looks like they weren't specifically raising the dig high to see the nickel ribbon interconnect here. So I think L4 was just the primary, possibly only target for this dig. And I suspect we're going to see the exact same thing for L6. So let me get drawn and measuring on that guy. Okay, here is our second window on this side, centered over L6 as expected. This one is also kind of interesting. It's wider, but also it doesn't go as high up on the module as the other windows we've been looking at. You can't actually see the connections to the nickel ribbon interconnect. So obviously they weren't looking at that, at least here. Okay, one more window. This is a big one. All right, not the best artist rendition of the dig site in the world, but good enough. And it looks like we were actually after two transistors here, Q5 and Q7. I think this one dig site was going after both of those. There are other components like R11, FT19, which is a feed through, and R12 that got caught in the crossfire, but I strongly suspect that Q5 and Q7 were the primary targets here. So interesting, we had Q5, Q7, and then down here, Q8. 3 transistors that all got dug upon, as well as 2 inductors. So I will be very curious to see if these are related in any way when we take a look at the schematics, which we will do now. Before I start talking about the specific components that were dug on in these schematics, I'm going to do what I probably should have done earlier in this video and talk about what all is inside the rope driver module, what each of these circuits or subcircuits on the schematic are. If you haven't watched Mark's video about core rope memory and the rope reader that I built, I highly recommend that you go check that out, because if you've seen it, you will probably know what most of these circuits are as I describe them. So, going through the module, along the top here, these top 3 big circuits are known as either the rope return circuits or the rope gate circuits. These are actually acting as high-side switches for pairs of rope modules. So only one of these 3 will be activated at any one time, and the one that is activated will be able to source current to its corresponding pair of rope modules. We didn't talk about these basically at all in the core rope video on Mark's channel, because my rope reader only handles a single rope module at a time. And so for my rope reader design, I actually eliminated all of this high side switching. Next up, down here, we have the inhibit drivers. Each one of these is a constant current sink for 225 milliamps with a soft turn on caused by this inductor here. So when you enable one of these inhibit drivers, it will start pulling 225 milliamps, which is going to be sourced by the rope return circuit. Next to that, we have our set and reset drivers, which act on essentially the same principle, but they just sink more current. Each one of these sinks 450 milliamps. Next up, we have what is called the inhibit gate. This circuit essentially enables all of the inhibit drivers at the same time. You can see that it puts out these nets called 40331A and 40332A. Those are applied to the inhibit drivers here, and you can see that if this voltage isn't present, if the inhibit gate is not supplying 40331A or 40332A, this transistor in the inhibit drivers will not be able to turn on. Next to this, we have a series of power filters. Each one of these power filter circuits is designed to be able to deliver pulses of 450 milliamps for a couple of microseconds. Directly below these circuits, we have the clear driver. Now, the clear driver is another thing that we didn't talk about, but because of the way the AGC instruction cycle works, the computer sometimes needs to start a core rope read cycle and then abort it if it decides, oh wait, actually I'm not addressing core rope. So it uses 350 milliamps to do that, to reset every core. And then finally, down here, bottom middle, we have a pair of diodes and resistors, which are part of the clear circuit. These were actually not in the original design, but these were added because of cross-coupling issues between the set and reset drive wires and the clear wire. Interestingly, every Apollo guidance computer needed these diodes and resistors in order to work correctly. And so what they would do, and you can actually see this in the AGC that we restored, is that they just connected the diode and resistor across the backplane and wrapped it in heat shrink tubing so that they wouldn't short against anything. All right, so moment of truth. What components have they been digging on? They have been digging on L4, L6, both of which are inductors in the power filter circuits I was describing, Q5, Q7, and Q8, each of which are in the same rope return circuit, which is very suspicious. And even though these things look disconnected on the schematics, they're actually very tightly connected because L4 and L6 here are putting out BPL MX1 and BPL MX2, which is then used to drive this same rope return circuit. So it's all interconnected, and it seems very likely that something went wrong with rope return circuit 2 here, and they had to dig and figure out what happened. All right, time to run some tests. So I'm just going to be running through the procedures here. I will not be able to do the first few steps because we're missing page 3. So I'm going to be starting on step 3.1.4c, doing some resistance checks. I don't know what came before this. Apparently there were some other resistance checks. But I'm just going to run through what I have, and I will also be supplementing what's in here with other checks, like the diodes along here in the rope return circuits are not explicitly tested, but they're easy to check, so I'm going to do so. So let's go. Okay, so 3.1.4c of the 200 ohm resistor checks, all good. The next step is more resistance checks, but what they're actually doing is they're testing the clear diodes here, and they're using a resistance check rather than a diode check for that. I'm going to switch it up and just do a diode check. So the test current, the diode test current for this multimeter is a milliamp going through 220 ohms, so I'm expecting to see 0.8 maybe for the diode check. So let's set up for that. Should be good. Okay, so we are looking for a diode from 138 to 140. Oh, we're beeping. Okay, and 0.8, yes, right on the dot, exactly as I thought. Okay, so that's good. And then if I reverse the polarity, yeah, open. Okay, so that diode is happy. And the resistor is also reading roughly correctly based off of the diode voltage that we saw. So both of these components are happy here and here. And then we'll do the same thing for the other one. Okay, and like I mentioned, while I am in diode test mode, I'm going to go through and use these test points that are not connected in the actual computer to check each one of these diodes. Not because I don't trust them, but I've had a complicated history with diodes, so I'm gonna check them all anyways. Okay, good news. As expected, all of the diodes in the rope return circuits are healthy. I am also going to check this one while I'm at it. And 102. Yeah, 3.3 volts sounds fine. I did see that there are some resistances that I can check. Okay, yeah, there's a couple things that I can check. So I can check on the rope return circuits. R3 and R1 are between pins 164 and 137. So I can measure that and make sure that the sum of those is 1970. And I can do that for each of the rope return circuits. I can also check R2 and R5 in parallel down here to be, what, 650? I can check these pull-up resistors on the inputs to these circuits, like R26 and R30. However, because those are pulled up to B+1 or B+2, I'm going to need to have the positive end on the input power filter circuit, and so I'm going to have the series DC resistance of L10, this 8.2 microhenry inductor, in series with my measurement. So I need to go look up in the spec what the expected DCR of that inductor is. Okay, so if we look up our 8.2 microhenry inductors in the parts table here, we see that all of them are part number 1010406-7. And if we pull up the specification control drawing for 1010406 and look up -7 in its table, we see that the maximum DCR for this inductor is, what, 1.32 ohms? So essentially in the noise. So we can just pretend that inductor is not there for our tests here. So that makes this nice and easy. Okay, and now, are there any other cheeky resistors that I can measure? Ah, yes, I can measure the output of the inhibit gate, 40331A. I should see a 2K to ground there. So, 2K. Cool, cool. Anybody else? I don't think so. Okay, I think we have completed our resistance checks, which means it is time to move on to capacitance. All right, so for capacitance, we are starting with 6.8 microfarad capacitors. Our first one is going to be pin 165 to 267. We're actually including the inductor in this measurement, but again, it's so small it probably doesn't matter. Okay, so we're reading 7 microfarads, and capacitance between the following pin pairs shall be 6.8 plus or minus 1. Yeah, I would say that's plus or minus 1. Okay. So all of the 6.8s are good. Now we are looking for much larger capacitances. Why is that? So we're looking at this circuit here. More filters, F, G, and H are the pins in question. Now, if we look at the table down here, pin G, this guy, is always pin 101, and pin F is always pin 102, which means we're going to be seeing these 3 caps essentially in parallel. Now the interesting thing is that we're measuring from 202, 203, 204. Okay, which are the output pins, which are separate, 202, 203, 204. Okay, so we have 21.99, and that is in spec. So all of these capacitors are good. And then last one, capacitance between 103 and 225 shall be 1 microfarad. And we're looking at this capacitor up here. Yeah, okay, yeah, 1 microfarad. Okay, all the capacitors check out, which is not surprising. There's never capacitor issues in flight Apollo hardware. I don't think I've ever seen a capacitor issue. So last thing is we need to check some inductors. We're going to actually check the inductance of most of our 8.2 microhenry guys. So 8.6 microhenries is well within spec here. We're looking for 8.2 plus or minus 2. 165. Yeah, I had already put a green check mark there, but it is actually inducting, so that's good. 266. So that's two of our circled components here, by the way. L4 and L6 that both look like good inductors. I'll take those measurements again, just to be sure, now that I'm looking at the schematic and see that I had put those in red circles because they were dug upon. But I didn't pick up anything weird in the tests for those, so that is very good news. Okay, so that's all of our inductors. Let's take one more pass on our problem children here. So our two problem children on this side of the module, L4 and L6, both reading as you would expect. No problems with the inducting, no problems with the conducting. They seem fine, which is good news. I don't really have a clear idea of why they would have been digging on both sides of these inductors if not to replace them. So I suspect that they did get replaced and are now testing correctly. So that is the end of unpowered testing. The module has passed with flying colors. So next up is wiring this thing up and applying power to it for the first time. All right, finally time to run the dynamic tests. I've gone ahead and wired up all of the connections that are necessary for all tests according to section 4.2.4.1 here. So we have a bunch of ground connections, a bunch of 14-volt power connections, and a bunch, or rather, 2 4-volt power connections. And then there are other things that we're going to have to connect throughout the course of the tests, but we'll get to those when we get to them. I have also set up a transistor driver here. This is in place of what I'm supposed to be doing, according to the test here, which is using a micrologic gate to drive the input pins. I don't have one of those, and so I've basically just made my own little RTL logic gate using a 2N2222 transistor. The first thing that we're going to test is the inhibit gate, of which there is only one in each module. So I am going to go ahead and wire up the rest of the things that need to be connected for that. Specifically, what I'm going to need to wire up is the input pin, pin 249, the output pin on 244, and then pins 104, 125, 224, and 212 also need to be grounded because those are the enable pins for the set and reset drivers and the clear driver. And allowing those to float would cause them to turn on and potentially damage themselves. So for every test that does not use those pins, we're going to be asked to also ground those. So the inhibit gate wires and the enables for the set, reset, and clear drivers are all wired up. I've wired up power to the power supply, put on a lot of current limiting, and we're just going to try to turn this thing on with basically everything disabled, just as a smoke test. I'm not expecting a lot of current to be drawn when I do this. This is sort of the moment of truth for whether we proceed any further or not. Okay. And looks like I picked a good current limit, but we're sitting at 14 volts and 4 volts on our 2 channels. It is drawing 40 milliamps idle, which I think is fine. So, good first test. Now, let me get the scope wired up. So, the way that I have this set up, I'm using a function generator that's just off screen over this way to manually trigger pulses into my little micro logic simulator circuit. I need to turn on power to the function generator first to turn on that transistor. And then we're going to turn on power to the module. I'm going to bump up the current limit here to, we'll give it 400 milliamps as a current limit. It should be just enough headroom. And so now I should just be able to trigger. Boom, look at that. We are expecting to see an output of about a diode drop less than 14 volts. According to the scope, 13.25 max on this. Give it a couple more shots, but it looks like our inhibit gate is working perfectly fine. Yeah, nice and clean. So next up is the inhibit drivers. So I'll turn off the inhibit gate basically, and then we'll switch over to the inhibit drivers and try all 8 of those. So I'm all wired up to test the first inhibit driver out of 8. This one is a little bit more complicated. Here is the procedure step that we're running. So in addition to pins 104, 125, 224, and 212, the inputs to the set and reset drivers and clear drivers being grounded to keep them from turning on, we also need to connect pin 260 to a potential of 1.7 volts below B plus high, which is 14 volts. So we're taking pin 260 to 12.3 volts. Now the reason for this is that the voltage used to control the driver transistor is actually supplied by the inhibit gate, which we just tested. The reason that they do this is so that the inhibit drivers can be set on or off according to the current memory location being addressed without turning them all on. And then when it is time to actually run a rope cycle, the inhibit gate is turned on, which supplies power to the inhibit drivers so that then they draw current through the enabled inhibit lines. These tests are set up so that we don't test multiple things at the same time. We've already tested the inhibit gate, and we don't want to cross-contaminate behavior of the inhibit gate with our inhibit drivers here. So we are just supplying the 12.3 volts that would be coming from the inhibit gate directly from the power supply. The setup is also a little bit more complicated now because we are testing a current driver and not a voltage switch like we were with the inhibit gate. The current drivers are sinks, so they want to sink 225 milliamps in this case. The way that we're measuring it is we have put a precision 0.1% 10 ohm resistor between 14 volts and the output pin of this circuit. So in order to measure current, we need to look at the voltage across that 10 ohm resistor. And neither side of it is going to be ground, right? It's 14 volts and then whatever the voltage on the output of the driver is. So therefore, we need to use a differential probe. So I'll give you an overview of the setup here. So here's our module with all the wires going in. The input driver is here, and then we have the load 10 ohm resistor and the differential probe that is being used to measure that, and then function generator over there generating the input pulse to enable the circuit. One other thing that's notable specifically about this first inhibit driver is that the procedure has an error in it. If we look at the input-output table here, it says pin A input is 269 and pin B output is 169. That is a lie. The pin B output is 168. 169 is chassis ground. So everything else in this table is correct, but that was surprising to find an error like that. I'm curious if they fixed this in later revisions. All right, so function generator on. I'm going to turn on the power supplies, only the 14 volts and the 4 volts at first, just to keep the inhibit drivers all definitely disabled. We'll make sure the module powers up fine. And yeah, 38 milliamps looks good. So now I'm going to turn on the 12.3 volts to give power to all of the inhibit drivers. And 225 milliamps is a really big idle current. That's almost like one of the inhibit drivers is stuck on, because each of the inhibit drivers is 225 milliamps. That doesn't really make sense though, because the 225 milliamps is going to be drawn from the 14 volt rail and not the 12.3 volt rail. So what gives? Oh, okay. So when the when the inhibit drivers are off, the transistor on the input, Q13, is on and pulling its emitter down to 40365A, which is effectively ground. Which means we're going to have current flowing through this 390 ohm resistor from 12.3 volts to maybe 1 volt. But the thing is, there's 8 of these circuits. So we have effectively 8 390 ohm resistors in parallel between 12.3 volts and 1 volt. And that sounds like a decent bit of current. Let me do some math. And yes, the math says that that should be 231 milliamps, which is a lot for idle current consumption, but what we just saw is actually exactly correct for all of the inhibit drivers to be off. So that's a good thing. It also maybe partly explains another reason why they would want the inhibit gate to only enable the inhibit drivers for a very short period, because man, they sink a lot of current when they're on. But it's fine for this test. This is what we're supposed to do. So let's get the inhibit drivers back on. 225 milliamps, nominal, apparently. And now let's trigger inhibit driver number 1. Ooh, that looks really good. The scope says max of 236.7 milliamps, which is quite high. We're expecting an output of 225 plus or minus 5 milliamps. So 230 is the upper end of what is acceptable at 25C. So I'm going to zoom in here. Let's get ourselves to 5 milliamps per div and drop down to minus 225 milliamps vertical offset. In theory now, when I trigger this, the horizontal line on the scope, 0, right, the x-axis, should be 225 milliamps, and so we can look above and below that to judge how high or low this current driver is running. Okay, yeah, this is, I mean, it's a noisy measurement, right, but this is running really hot. The max is 233 or so that the scope is picking up, but it looks like it's actually centered around 231, 232 or so, which is actually out of spec high. This is pretty spicy. Yeah. All right. Well, let me set up for inhibit driver number 2 and see what happens. All right. Here's inhibit driver number 2. Oh man, also, this one's even spicier. This one's at like 233 on average, I would say. Inhibit driver number 3. Okay, that's, this one is extremely spicy. Yeah, so I wonder if all of these are component drift over time, just aging, or if it's something about this module that makes it particularly spicy. I guess it could also be measurement error if my probe is a little bit off. And number 4. See, this one is definitely within spec easily. Number 5. Very spicy. Number 6. Also pretty spicy. Number 7. And number 8. Number 8, which is fascinating. So, this is actually something that I was very, very curious to see. If you watched Mark's video about core rope memory and the rope reader, you'll probably be familiar with the parity inhibit wire. The parity inhibit was the original idea, or an original idea, that they had on how to reduce the amount of current that they needed to use for all of the inhibit wires. And it worked well on block 1, and then on block 2, they made an oopsie, and that resulted in one of the cores not being fully inhibited on basically every read cycle. They ended up having to use one of the reset wires as an additional inhibit, but under the original scheme, in order for the parity wire to work, it actually had to carry more current than all of the other inhibit wires. However, once you start using that reset wire as another inhibit, the parity inhibit doesn't actually need to be 300 milliamps anymore. It can just remain at 225 like all the rest of them. And that's kind of what this specification here suggests. This table for the inhibit drivers just says 225 milliamps for all of them. It doesn't make any mention at all of a 300 milliamp inhibit driver. So it seems like the schematics were just outdated for the entire program, and they just said 300 milliamps for this driver, but it seems pretty clear that it has been tuned to 225 milliamps. It's running spicy like all the other ones, but it's definitely 225. In my own rope reader, I run my parity inhibits at 225 milliamps for that reason, because it's not necessary to do it at 300. Now we're getting into the higher current stuff. So I've rewired to test the first set or reset driver. I no longer need the 12.3 volt rail for the inhibit drivers, so I have removed that. This is what we're testing for the set and reset drivers. We're putting in 0.8 to 2.1 volts, and we're looking for 450 milliamps plus or minus 5. So let's get going. Everything looks good there, and now we're ready to trigger. Boop. That looks pretty good. Yeah, look at that. We're actually a bit low. It's within spec for sure. It's hanging out, I would say, what, 446 milliamps or something like that? Barely within spec, but on the low side. Set reset driver number 2. Okay, also reading slightly on the low side, maybe very slightly higher than the other one. And number 3. This one is definitely closer to the middle than the others. Yeah, so these are, I would say that all the set reset drivers are within spec, like slightly low, but within spec, which is very interesting compared to the inhibit drivers, which are they're all high, barely within spec or out of spec. I think that means that, well, I don't know what that means. It'd be easier to blame diode aging or something if they were all drifting in the same direction, you know? Next up, we have the clear drivers. The clear drivers are kind of interesting because the way that they're implemented is a little bit different. There is one clear driver per pair of rope modules, which means that between the 2 rope driver modules in the Apollo guidance computer, they only need 3 circuits. So there's going to be a spare one. So the way that they have it set up is that each module has 2 clear current drivers that are both driven by the same enable. And for one of the modules, one of the current drivers is not connected to ground. And so it can't actually be enabled. And then in the other rope module, they're both connected to ground, so that both of them are able to drive current. Now looking at the test procedure, this is a miss. They never actually say to connect that ground pin for the second current driver anywhere in this test procedure. So if you miss it, it's going to look like it doesn't work. And this is what we're looking for. We're putting in a 4 microsecond pulse, and we are looking to see 350 plus or minus 5 milliamps on both of the outputs of the clear circuit. So as with the others, let's just get an overview, look at the waveform. It looks pretty clean, but the max is reporting 376.7 milliamps, and I think that is probably accurate based off of what I'm seeing. I don't think that's the fault of noise, so That's pretty high. Wow, yeah, that is... it's going off the top of the screen, it's so high. Yeah, so instead of 350 milliamps, we have 370 milliamps on this current driver, which is crazy out of spec. And here's the other one. Okay, so this one is only going to like 365 milliamps, which is still obviously way higher than it should be, but slightly less bad. But yeah, these are both way out of spec. Maybe this is why it got scrapped? Okay, well, that's it for the current drivers. All right, time for the last type of active circuit, the rope gates. Now these are not current drivers like everything we've been testing. These are high side switches, and so we will be looking not at current, but at voltage. Additionally, every one of the 3 rope gate circuits has 3 strings of outputs, each of which have 3 or 4 actual outputs through diodes. However, the way that they built the rope module, there are test points on each of the 3 strings that are not connected when the module is plugged into an actual computer, but they are used at this phase of testing. Now the procedure calls for a very particular load resistor here. We have 31 ohm plus or minus 1% for each of our 3 outputs. This is not a common type of resistor. There were none available on DigiKey, and I think exactly 1 vendor on Mouser, but I got them. And so I have hooked up 3 of them here to the 3 outputs of our first rope gate. I'm going to be testing them in the order of 1, 3, 2, because number 2 is the one that is suspect. According to the procedure, we need to be looking for an output of 0 volts essentially when it's off, and 1.5 volts below B plus max when on. That is going to be 12.5 volts that we're looking for. I have scope probes on all 3 channels. I think everything should be good to go. Rope module, power on, and trigger. Okay, we have a fully working rope gate. All 3 channels are jumping up to 12.4 max, 12.267 max for channel 2. I mean, it's all essentially fine. We were not actually even given error bounds on this measurement. It just needs to work. Rope gate number 3. That looks pretty good to me. All right, moment of truth. Rope gate number 2. It works. Perfectly functional, just as good as the other rope gates. This is not surprising to me really, but it does strongly suggest that when they went digging, they did find and fix the problem with this circuit. So, good news. We have passed, asterisk, all of our functional tests. The static tests were all good. The dynamic tests, everything works. We have some things out of range. So, what have we learned? Well, for starters, I went into this expecting that by the end, we would either know for sure why this got scrapped, or have absolutely no clue. But somehow we've ended up with option 3, where all of the circuits work, but a lot of them are out of calibration, some of them very far out of calibration. And honestly, I have no idea if this is why it got scrapped, or if it is just because this thing is 50 years old. It's worth noting that all of the circuits that are out of calibration will have absolutely no effect on the operation of this module. Installed in an AGC, it would be able to read ropes just fine. It would just draw more power than it needs to while doing so. Unfortunately, this is our only data point for how these modules age. I went back and found some pictures from the AGC restoration, like this one, and in this picture you can see that back then I was just checking the voltage outputs from all of the current drivers. I wasn't actually looking at the current, because all I wanted to do was verify functionality. I wasn't after calibration. So I don't actually have any current numbers from the AGC that we restored. So this is all that we have. So unfortunately, it's going to remain a bit of a mystery, but maybe it was the calibration that got it scrapped. The second thing that we learned is that the inhibit parity driver got reduced from 300 milliamps to 225 milliamps as part of the fix for the Block 2 parity wiring problem. This was honestly super exciting for me to see. I've wondered about this ever since I built my rope reader. I didn't actually know about the Block 2 parity issue until I built my rope reader, because the fact that that happened did not come down to us through any surviving documentation. I basically had to put together the puzzle pieces to figure out why they made the wiring changes that they did. And so it's not surprising that the current set point changing also didn't come down to us, but super cool to see it. Lastly, this module gave me the opportunity to compare the current waveforms from a real rope driver module with my rope reader. So here's a snapshot of the set driver from the real rope module, and here's a snapshot of a set driver from my rope reader when I was bringing up the first board. I'm actually super happy with how close these two are. The main differences that I can see are that the real set driver shuts off much more sharply than my rope reader does, which is totally fine. There's absolutely no problem with my rope reader being slightly slower to turn off there. And then also, kind of interestingly, the rope reader has more wobble on the rising edge. I suspect it's because the closest inductor I was able to find isn't quite perfect, but it's close enough. I don't think this wobble has any negative effects. Anyways, this turned out to be way longer than I was expecting, so I hope I didn't bore all of you out of your minds, and I will see you next time with more Apollo hardware.